Hello, everybody. This is tutorial 8, and I'm going to share my screen. Okay, you should be seeing tutorial 8. And this one's a little bit challenging because it's in 2 dimensions. And what we're seeing is a top view of a frictionless table. We're looking down on it as if we're a seagull looking for a target. And these 2 blocks are connected by a massless spring. And then we're told that the 2 blocks are pulled apart so that the spring is stretched. And then we push the 2 blocks down the table so that they start with the same velocity down the table. And we let go of both blocks at exactly the same time. Now we're told that block A is 2.5 times as big as block B. So what you should be seeing is these blocks moving down the table, and they would be going at constant speed down the table. But as they go down the table, they would be oscillating in and out, in and out, in and out because of this spring bouncing them back and forth. Now, we're asked to draw separate free body diagrams for each block immediately after the release of the blocks. Now, in the vertical direction, we have weight down on A and a normal force up by the table on A. And likewise, we have a weight force down on B and a normal force by the table on B, but no friction because this is a frictionless table. Now, because this is a massless spring, there's no force acting on the spring. In the horizontal direction, if the spring is stretched, then it's going to be pulling to the right on A, a force by the spring on A, and it's going to be pulling to the left on B. Now, I know I told you never to draw a free body diagram for a massless string or a massless spring. We're just going to do it one more time. We know that if the spring is massless, the poles at both ends have to be equal to each other. This would be the force by A on the spring, and this would be the force by B on the spring. Now, because Newton's second law is mass times acceleration, if the mass is 0, the net force has to be 0. And so that means that these have to be equal to each other. Now, we know that these are third law companions, and these are third law companions. And so what we're really interested in is how hard does the spring pull on A compared to how hard it pulls on B? And the answer to that is that the pull by the spring on A has to be equal to the force by A on the spring by third law. That has to be equal to the force by B on the spring, and that's going to be by second law with 0 mass, and that's going to be equal to the force by the spring on B, and again, that's by third law. So if I look at these vertical forces, they balance. They balance each other out, and so I get no net force in the y direction on A and B. But in the x direction, I have an unbalanced force on each block. And so the net force on A is just this force here, and the net force on B is just this force here. And so that means that the net force on A has to be equal to the net force on B. Well, that's not entirely true. That's halfway true. The magnitudes have to be the same, but if I'm considering the vector quantities are equal in magnitude, but opposite in direction. So there's this minus sign there, because this one's to the right and that one's to the left. And so whatever net force A has, B has to have the same size net force, but in the opposite direction. And this holds true for all times. And that's because Newton's third law applies at all times. It's always going to be equal and opposite. Now, we're told that the initial velocity of the two blocks is in this direction. We'll call that the negative y direction. And it's 1, 2, 3, 4 squares long. I don't know whether those squares represent meters per second or miles per hour. It's not important. It's just some unit. Now I know that by Newton's second law, I can write that acceleration as the change in velocity over the change in time. And so that means that the net force has to always be in the same direction as delta V, and hence the acceleration. So that means, if we remember what we said here, the net force on A when the spring was stretched was to the right, and on B it was to the left. So if we look at the change in velocity, that's going to have to be to the right on A, and I'm just going to arbitrarily make that 2 squares long. Okay. And I do that because I know that whatever change in momentum I have for A, I have to have the same change in momentum for B, but in the opposite direction. We learned that in the last tutorial. Well, that means that the mass of A times the change in velocity for A has to equal the mass of B times the change in velocity of B with a minus sign. Well, if the mass of A is 2.5 times bigger than B, then the change in velocity for A has to be 2.5 times smaller in order for this to be equal. So if I have 2 squares for A, I'm going to have 5 squares for B. That's 1, 2, 3, 4, 5. And it's got to be in the opposite direction. Okay. These are the same in magnitude. Opposite in direction. Would this comparison change if we considered another time interval equally small occurring later? No change. What about a much longer time interval? No change. We did not, in our use of Newton's second law, make any assumptions about the size of the time interval. Okay, now if we use our knowledge of the velocities and the changes in velocities to construct momentum vectors and change in momentum vectors. So that's easy enough. The momentum is just defined as the mass times the velocity. So the momentum of A is just the mass of A times the velocity of A, spelled with an A, okay? And the change in momentum for A is just equal to the mass of A times the change in velocity of A. So we just need to take these vectors up here and multiply them by the mass of block A and the mass of block B. But here's the thing, we weren't given masses. All we were told is that the mass of A was 2.5 times the size of mass of B. So in order to stay within the size of this grid, I'm going to choose the mass of B to be 1 unit. Kilograms, grams, whatever you want to assume. That means the mass of A has to be 2.5 times bigger. We'll call that 2.5. Because 2.5 is 2.5 times bigger than 1. Now, my initial velocity was 4 in the negative y direction. So if I take that velocity of -4 in the y direction and multiply it by 2.5, I'm going to get a momentum vector that is 10 units in the negative y direction, because 2.5 times 4 is 10. But when I take that same velocity of 4 in the negative direction and multiply it by the mass of B, which is only 1, I get a vector that's only 4 long. Because 4 times 1 is 4. Now, we can do the same thing with the change. Oh, I'm sorry, that wasn't showing. Okay, so this one is 10 in the negative y direction. This one is 4 in the negative y direction. Now, if we do the same thing with the change in momentum vectors, I have to take this change in momentum for A. I spoke wrong. I said wrong. I have to take this change in velocity for A of 2 to the right and multiply it by the mass of A, which is 2.5. Well, 2 times 2.5 is going to be 5 units to the right. 1, 2, 3, 4, 5. And if I take this change in velocity for B of 5 units to the left and multiply it by the mass of B, which is 1, I'm going to get 5 units to the left. 1, 2, 3, 4, 5. And this is what we were expecting, right? Because we said that whatever change in momentum A had, B had exactly the same change, but in the opposite direction. Well, A has a change of 5 units to the right, and B has a change of 5 units to the left. 1, 2, 3, 4, 5. Now, the final momentum is just what I started with, plus the change. Okay. So if I take my initial momentum for A, and add to it this change of 5, 1, 2, 3, 4, 5 to the right, I'm going to get a final vector that looks like this. And so that's going to be plus 5 in the x direction and minus 10 in the y direction. Now, with B, I started with 4 in the negative y direction, 1, 2, 3, 4. And then the change vector was 5 in the negative x direction, 1, 2, 3, 4, 5. So this final vector is going to look like this. And that's going to be negative 5 in the x direction and negative 4 in the y direction. Okay, so let me just remind you what we did. We started with velocity and change in velocity. By multiplying those by the masses, we got the momentum and the change in momentum. And then if we took that initial momentum and added the change, we were able to get the final momentum. Now, if we go to page 3, we're asked to combine A and B into a single system that we are going to we're going to call A plus B. So C is equal to A plus B and the spring. But we'll find that the spring not very exciting. Okay, so the vertical forces on this system are just the gravitational force on C. And we know that that's the combined weight of A and B. And we also have this normal by the table on C, and that's the combined push up by the table on A and B. Now, the horizontal forces, I got nothing. And that's because all of those forces are internal forces. I've got the force by spring on A and the force by A on the spring. And those are equal and opposite by third law. And I have the force by the spring on B and the force by B on the spring. And those are equal and opposite by third law. Those are internal forces if I'm looking at the combined system of C. And just like we don't draw the force by my liver on my spleen when we're drawing the free body diagram of the Greg, we don't draw any internal forces on our free body diagram. And so that means my net force on C has to be 0. Now, if we write an equation for the momentum of C in terms of the momentum of the constituent bodies, that's just going to be the momentum of A plus the momentum of the spring. Okay, that's just wrong. That's just sickening. I don't know why we call momentum P, but momentum of C is going to equal the momentum of A plus the momentum of B plus the momentum of the spring, but because it has no mass, that just doesn't add anything. So it's A and B. Now compare the momentum of system C immediately after the blocks are released to its momentum at the following times: a short time later or a much longer time later. Well, there's going to be no change either way. And the reason for that is that the final momentum of C is just going to be the initial momentum of C plus the change in momentum for C. Well, that's going to be the initial momentum of C plus the change in momentum of C, I can write as the change in momentum of A plus the change in momentum of B. but I know that these two are equal and opposite to each other. So that is 0. And so I just end up with the initial momentum. The final momentum is equal to the initial momentum. And that's what we mean when we say the momentum of the system is conserved. So this is what we found out in tutorial 7. If the net force on the system is 0, then the change in momentum for C is 0, and momentum is conserved. Imagine a single object whose mass is equal to the mass of system C, and whose momentum is equal at all times to the momentum of C. Draw an arrow that represents the direction of the velocity of that object. Well, if the momentum of C initially was the sum of these two things, well, that's just in the negative y direction. And if that doesn't change throughout the whole process, then what we end up with is a total momentum in the negative y direction. So that means since the momentum of C is just equal to the total mass times the velocity of the center of mass, the center of mass must always be in the same direction as the total momentum of C, which is in the negative y direction. Now we're to the last page, and here things get a little more complicated. We disconnect the spring to B so it's no longer stuck on B. And now that spring is just acting like a bumper car bumper. And so it kind of dangles off of A, but B is just all by its lonely. And we ram these two together with these initial velocities, and the spring causes them to bounce apart. And so we don't have that oscillation going anymore. We just have them coming in and bouncing off. What are the external forces on C? Well, in the vertical direction, we have weight down and the normal by the table up, just like before. But they cancel each other by Newton's second law with 0 acceleration in the vertical direction. In the horizontal direction, we got nothing. Okay, and that's because all of these forces are internal forces, like we talked about before. And so the net force on C is going to be 0 once again. Now, this is perhaps the most challenging part of this tutorial. We're told the momentum of A before the collision, and if I count these squares, what I get for the block A is 9 squares in the x direction and 5 squares in the negative y direction. We do the same thing. We're given the same information for B, and what we see there is that we have 1 square in the negative x direction and 2 squares in the negative y direction. Now, system C is just going to be the sum of the momentum of A and the momentum of B. If I do it with numbers, it would be 9 minus 1, or 8 squares in the x direction, and negative 5 plus a negative 2, which would be a negative 7 in the y direction. Now, I can also do it graphically. If I take the momentum of B and add it to the momentum of A, there's the plus sign right there. My total momentum is just going to be this vector that goes from here to there. Okay, that would be the momentum of C. So if I draw it over here, it would be oh, I did something wrong. So it would have gone here. Yeah, I did that one wrong. So let's do it right over here. 8 over 1, 2, 3, 4, 5, 6, 7, 8. And 7 down, 1, 2, 3, 4, 5, 6, 7. It's going to go to right here. So my total momentum for the system would be like that. Now, the next words that I say are the most important things I'm going to say about this tutorial. And that is the momentum of the system has to be conserved. That just means stays the same. So that means it has to, once again, be exactly this. And that means that the change in momentum for system C is just going to be a big fat 0. Okay. Now, there are many ways to get the momentum of A after the collision. But I like to go about it this way. If I take the momentum of block B before the collision, that's going to be down 1 and over down 2 and over 1. That'd be P initial for B. And the final momentum is 1, 2, 3, 4, 1, 2, 3, 4, and down 2. So it's going to be like this. That'll be P final. Now the change vector is what I have to add to my initial to turn it into my final. And so the change for B is going to be 5 squares to the right. And that means that the change for A has to be 1, 2, 3, 4, 5 squares to the left. So if I take my initial block, my initial momentum for block A, which was 9x and negative 5y, if I had a change of negative 5 squares in the x direction, that's going to leave me with 9 minus 5 or 4 squares in the x direction and 5 in the negative y direction. So I would go in the x direction 1, 2, 3, 4, and then go down 5, 1, 2, 3, 4, 5. So that's going to be a vector like that. Now, I could have also started with this vector. If I just brought this initial, this would be P final for A. If I had taken this initial vector of momentum for A and added the change, I would have gotten the same thing. So let's do that. This is 1, 2, 3, 1, 2, 3. So this would go to here. So all I've done here is I've just taken this vector we were given by the problem, and I moved it down here. And if I add this change that we calculated, that's 5 to the left. So this would be P initial for A, and this would be the change in momentum for A. The initial plus the change gives me the final. So again, the one that we need to draw for this is that one there. And the one that we need to draw here is 5 to the right, and this one 5 to the left. Okay, now remember, the way we define the center of the velocity of the center of mass is that the momentum of the system C is equal to the total mass times the velocity vector for the center of mass. Well, since the total mass is just a positive number, these two vectors will have to be in the same direction. So whatever direction I have for my total momentum of the system, my center of mass has to be going in that same direction, both before and after. Now, that center of mass is it's a construct. It's an idea. You can't see the center of mass of this system. It's an invisible point that we'll show you in a couple of weeks how to calculate where it is. But what we know is that if we define our total momentum this way, this velocity is also conserved throughout a collision. Okay, well, that's the tutorial. I hope it was as fun for you as it was for me. And we're going to stop sharing, and we're going to stop recording. Have a great day.